A proposed design of a cantilever retaining wall is shown in figure below. The unit weight of the concrete is 24 kN per cubic meter, and 1991-1-1:2002, and the soil has weight density 18 kN per cubic meter. The soil peak strength parameters are angle of shear resistance, phi, equals 38 degrees, C equals 0. The retained soil carries a uniform surcharge of intensity 10 kilopascals. Ignore any passive resistance from the soil in front of the wall. Check the safety of the proposed design against the GEO. Design Approach 1. Limit state of overturning and sliding according to Eurocode 7. Solution. Take unit weight of concrete to be 24 kN per cubic meter. Sin of angle of shear resistance is equals to 38 degrees. Facto or active pressure equals 1 minus sin of angle of shear resistance divided by 1 plus sin of angle of shear resistance. Active pressure equals 0.5 multiplied by the factor of active pressure multiplied by soil unit weight, 18 kN per cubic meter, multiplied by the square of the retained height, which is equals to 5 meters. Surcharge pressure equals active pressure multiplied by surcharge load multiplied by retained height. Remember, active earth pressure has triangular force diagram as shown in figure above and thus acts at a distance of retained height divided by 3. On the other hand, surcharge pressure has a rectangular diagram and thus acts at a distance of retained height, h divided by 2. Overturning moment is given by summation of moment due to active earth pressure and moment due to surcharge pressure about the toe of the retaining wall. Overturning moment will be equal to 53.55 multiplied by 5 over multiplied by 11.9 multiplied by 5 over 2. Let's find out the stabilizing moments acting due to base weight, soil weight, and stem weight about the toe of the retaining wall. Moment due to base equals to unit weight of concrete, 24 kN per cubic meter, multiplied by area of the base, 3 times 0.4, multiplied by distance of the center of the base from the toe of the retaining wall, that is horizontal distance from toe to center of the base, which is 1.5 meters. This gives 43.2 kN meters. Moment due to stem equals to unit weight of concrete, 24 kN per cubic meter, multiplied by area of the stem, 0.4 times 4.6, multiplied by distance of the center of the base from the toe of the retaining wall, that is horizontal distance from toe to center of the base, which is length of toe, 0.5, plus half of 0.4 meters, which is 0.7 meter. This gives 30.9 kN meters. Moment due to soil on heel of retaining wall equals to unit weight of soil, 18 kN per cubic meter, multiplied by area of the soil, 4.6 times 2.1 meters, multiplied by distance of the center of the soil from the toe of the retaining wall, that is horizontal distance from toe to center of the base, which is given by length of toe, 0.5, plus width of stem, that is 0.4 meters, plus half of 2.1 meters, which give a total of 1.95 meter. This gives 339.1 kN meters. Total resisting moment is equal to summation of stabilizing moments, that is 43.2 plus 30.9 plus 339.1 kN meter. Factor of safety against sliding equals total resisting moment divided by overturning moment equals 413 divided by 119, which gives the factor of safety against overturning to be of 3.47. Let's find position X, which is the position of stabilizing force due to ground bearing pressure. Position X is given by the difference of stabilizing moments and destabilizing moments divided by sum of vertical forces. Vertical force is due to base is equal to unit weight of concrete multiplied by area of base, that is 3 times 0.4, which gives 28.8 kN. Do the same for stem and soil to get 44.2 and 173.9 kN respectively. Therefore, total vertical forces is equal to 28.8 plus 44.2 plus 173.9, which equals 246.9 kN. Difference of stabilizing moments and destabilizing moments is equals to 413.2 minus 119.1 whole psi gives 294.1 kN meter. 294.1 divided by 246.9 gives 1.19 meters. Considering that 1.19 meters is within the middle third of the base length, i.e. 3 meters, eccentricity of vertical force is given by half of the length of base minus 1.19, which is equals to 3 over 2 minus 1.19, which gives 0.31 meters. Maximum bearing pressure equals sum of vertical forces divided by base length multiplied by 1 plus 6 multiplied by eccentricity of vertical forces divided by length of the base of the retaining wall. Therefore, maximum bearing pressure is equals to 133 kilopascals. Remember, the safety bearing capacity of the soil was provided as 250 kilopascals. Factor of safety against bearing pressure is equals to 250 divided by 133, which gives 1.88. Let's do the same horizontal forces to find factor of safety against sliding. Total horizontal forces is the sum of passive pressure due to soil and surcharge pressure, which is equals to 55 plus 11.9, which gives 65 kilonewton. Diesel resistance is given by a product of total vertical forces and tan of phi, which is 38 degrees, which gives 192.9 kilonewton. Factor of safety against sliding is equals to design resistance divided by destabilizing horizontal forces, which is 192.9 divided by 65.5, which equals 2.95. The EQU, GEO and STR limit states are the most likely ones to be considered for routine design. Furthermore, in the design of retaining walls and foundations, it is likely that limit state GEO will be the prevalent state for determining the size of the structural elements. When checking the GEO and STR limit state requirements, one of 3 design approaches is used: Design Approach 1, Design Approach 2, or Design Approach 3. This choice of 3 approaches reflects the Europe-wide adoption of the standard and offers designers in different nations an approach most relevant to their needs. Design Approach 1 is the most likely method to be adopted in the UK. As mentioned earlier, the choice of partial factors to be used is dependent on the design approach being followed for the GEO and STR limit states. For each design approach, a different combination of partial factor sets is used to verify the limit state. For Design Approach 1, for retaining walls and shallow footings, 2 combinations are available, and the designer would normally check the limit state using each combination, except on occasions where it is obvious that one combination will govern the design. The combination of partial factor sets is different for pile foundations. Design Approach 1, using Table 1. Combination 1, A1 plus M1 plus R1. Combination 2, A2 plus M2 plus R1. In BSN 1997-1 UKNA 2.4.7.3.4.1, 1, P. The particular design approach to be used for STR and GEO limit states. Use Design Approach 1 only. The set of actions, denoted by A, material properties, denoted by M, and ground resistance, denoted by R, for each design approach are given in Table 1. Also given in the table are the partial factors for the EQU limit state. From Table 1, EQU limit state, i.e. overturning. Permanent unfavorable action has a factor of 1.1, while permanent favorable action has a factor of 0.9. Variable unfavorable action has a factor of 1.5, and coefficient of shear resistance is 1.1. Design material properties. Let's find the design angle of shear resistance. Design angle of shear resistance should be equal to inverse of tan into bracket tan angle of shear resistance divided by coefficient of shear resistance, or tan 38 divided by 1.1 to get design angle of shear resistance is 35 degrees. Substitute into the equation FO active earth pressure to get design active earth pressure is equal to 1 minus sin 35 divided by 1 plus sin 35, which equals to 0.271. Design actions. The weight of wall is a per net favorable action. Design action due to stem is given by area multiplied by unit weight of concrete multiplied by per net stabilizing actions from Table 1, which equals a product of 0.4 by 4.6 by 24 by 0.9, which gives 39.7 knots. Doing the same for base, you get 0.4 times 3 times 24 times 0.9 and 2.1 times 4.6 times 18 times 0.9 for soil to get 25.9 kilonewton and 156.56 kilonewton respectively. The thrust from the active earth pressure is a permanent unfavorable action. Find the design active earth press, shear, and surcharge pressure using factors from EQU Table 1. Design active pressure equals 0.5 multiplied by the design factor of active pressure multiplied by soil unit weight, 18 kilonewton per cubic meter, multiplied by the square of the retained height, which is equals to 5 meters, multiplied by factor of permanent unfavorable action from Table 1, which is 1.1. Thus design active pressure is equal to 0.5 times 0.271 times 18 times 5 squared times 1.1, which equals 67 kilonewton. Design surcharge pressure equals design factor for active pressure multiplied by surcharge load multiplied by retained height multiplied by factor of permanent unfavorable action from Table 1, which is 1.1. You get design surcharge pressure equals 20 kilonewton. Let's find design moments for both stabilizing forces and destabilizing forces. Destabilizing moment is given by 67 multiplied by a third of 5 meter plus 20 multiplied by a half of 5 meters, which is moment due to soil pressure and surcharge load respectively, summing to 162 kilonewton-meter. Stabilizing moment is equal to 39.7 times 0.7 plus 25.9 times 1.5 plus 156.5 times 1.95, which equals 371.8 kilonewton meters. We can conclude that the EQU limit state requirement is satisfied since the sum of the destabilizing moments is less than the sum of the stabilizing moments. Overturning design is equals to 371.8 divided by 162, which equals 2.3.